Hello everyone, my name is Ayush. Today I will be presenting our breast cancer classification project along with my teammate Samir Hussain, where we apply classical machine learning algorithms to identify malignant versus benign tumors. The presentation will walk through the full pipeline starting from data pre-processing to model evaluation. So we're going to start off with problem overview. The aim of this project is to predict whether a cancerous growth is malignant or benign using machine learning. The dataset contains various clinical features such as radius, texture, smoothness, area, mean, extracted from cell nuclei images, which will be used for classification. Talking about the dataset, it contains 569 samples and 30 numerical features. After inspecting the data, we confirmed there were no missing values. As you can see on the image, each column has all the required fields, so there are no any missing values. Now we will move forward with the data pre-processing. We cleaned the dataset by removing non-useful columns and converted the target labels to numeric form. Since our models are sensitive to scale, we used standard scaler to normalize the features. We plotted a heat map using correlation matrix from which we filter out the columns having correlation more than 92%. By doing so, we were able to reduce the columns to just 23 instead of 31 by dropping 8 highly correlated columns. To evaluate models fairly, we split the dataset into training and test sets using an 80:20 ratio using train-traced split package. And now we will go over the algorithms that were implemented in this project. We used 7 machine learning algorithms and compared their performance on accuracy, confusion matrix, and ROC curves. We will now go through each of them one by one. So the first off, we're going to start off with logistic regression. This is a simple yet powerful linear model commonly used for binary classification. It works by estimating the probability that a tumor is malignant using a sigmoid function. Logistic regression is fast, easy to implement, and usually provides a strong baseline in medical classification problems like ours. Talking about its result, it performed extremely well, achieving a training accuracy of about 98.7% and a test accuracy of 97.4%. The confusion matrix shows 70 true negatives and 41 true positives, which means the model is correctly identifying most cases. The key areas to look are the false negatives, which represent missed malignant cases. We only have 2 false negatives, which is a very low number and crucial for medical applications. The precision and recall values also show a strong performance, especially recall of 0.95 for malignant cases, meaning the model successfully identifies most cancer-positive samples. The next up is KNN or K nearest neighbors, which is an instance-based learning algorithm. Instead of training a traditional model, KNN makes predictions by comparing a new sample to its nearest existing samples in the training data. The class with the majority vote becomes the prediction. Because KNN relies on distances, feature scaling is essential for good performance. It works well when similar data points form natural clusters. And now talking about its result, it achieved a training accuracy of about 97% and a test accuracy of 93.9%. The confusion matrix shows 68 true negatives and 39 true positives. Compared to logistic regression, KNN has more false negatives, specifically 4 false negatives, meaning it missed 4 malignant cases. The precision and recall scores remain solid though, ranging from 0.96 to 0.93 to 0.96. But the slightly lower recall for malignant cases suggests that KNN is not as effective at capturing all cancer-positive samples. This shows that while KNN performs reasonably well, it is more sensitive to data distribution and noise in the dataset. The next algorithm will be support vector machine or SVM, which is a margin-based classifier that works by finding the optimal hyperplane that separates malignant from benign samples. It does this by maximizing the margin between the two classes, which helps the model generalize well. SVM is especially effective for a high-dimensional dataset like ours. By using kernel functions, SVM can also capture nonlinear relationships, giving it a strong advantage in many medical diagnostics tasks. Now looking at the results of SVM, it performed exceptionally well on this dataset. It achieved a test accuracy of 98.25%, which is the highest among all the models we have seen so far. The confusion matrix shows 71 true negatives and 41 true positives with 0 false positives, meaning the model never incorrectly predicted a benign tumor as malignant. This is an excellent outcome. There were only two false negatives, which is very low and critical for cancer detection. The precision for the malignant class is perfect at 1, indicating that whenever the model predicts cancer, it's almost always correct. Overall, SVM is one of the strongest models in our entire pipeline.
Hello everyone, my name is Samir and I will be continuing the presentation from here. So talking about the decision tree classifier works by splitting the data set into smaller subsets based on feature thresholds, eventually forming a tree of decision rules. Each path represents a sequence of conditions leading to a prediction. Decision trees are easy to visualize and interpret, and they can capture complex non-linear relationships. However, they tend to overfit unless properly constrained, which can affect performance. Now, for the result, the decision tree achieved a training accuracy of 95.38% and test accuracy of 94.74%. The confusion matrix shows 68 true negatives and 40 true positives, but also 3 false positives and 3 false negatives. While the overall accuracy is solid, the model shows sign of slight overfitting because the training accuracy is higher than the test accuracy. Decision trees are flexible but can easily memorize pattern in the training data, which reduces generalization compared to SBM and logistic regression. This model has a higher number of false negatives, meaning it misses more malignant cases. Now, for the random forest is an ensemble learning method that builds many individual decision tree and then average their predictions. By using bootstrap samples and randomly selecting feature at each split, the model reduces overfitting and becomes like much more stable than a single decision tree. This makes random forest a strong choice for complex data sets, offering both high accuracy and robustness against noise. For the result, random forest achieve a very high accuracy of 99.56%, indicating that the model fits the training data extremely well. Its test accuracy is also strong and 96.49%, showing good generalization. From the confusion matrix, we have 70 true negatives and 40 true positives, and only one false positive but three false negatives, which means three malignant cases were misclassified. Although random forest outperforms the decision tree significantly, the near perfect training accuracy suggests some overfitting. Nevertheless, this model still performed very well overall. For the gradient boosting is another powerful ensemble method, but unlike random forest, it builds trees sequentially. Each new tree is trained to correct the mistakes of the previous ones by focusing more on misclassified samples. The boosting approach often leads to very strong predictive performance, especially on structured data sets like ours. However, because it leans in a sequential manner, gradient boosting can also overfit if the model is not carefully tuned. Coming to the result, gradient boosting achieved a perfect accuracy of 100%, which clearly indicates overfitting. Since no real world model should fit all the training samples perfectly, its test accuracy is still like strong at 95.61%. From the confusion matrix, we have like 69 true negatives and 40 true positives, but also two false positives and three false negatives. This means the model missed three malignant cases and incorrectly flagged benign cases as malignant. Performance wise, gradient boosting is one with the like random forest, but the perfect training accuracy shows that the model is more likely to overfit. Coming to the XGBoost is one of the most powerful implementation of gradient boosting. It improves on standard gradient boosting by adding regularization, which helps reduce overfitting. XGBoost also introduces several optimizations such as parallelized tree construction, handling of missing values, and advanced sampling techniques. It is widely used in industry and competition due to its ability to capture complex patterns and deliver top tier performance. For the result, XGBoost achieved a training accuracy of 99.12%, and a test accuracy of 95.61%. This is very similar to standard gradient boosting model, but with slightly better generalization due to built-in regularization. The confusion matrix shows 69 true negatives and 40 true positives, with 2 false positives and 3 false negatives. Like the gradient boosting model, it misses 3 malignant cases, which is key metric to monitor in cancer detection. Overall, XGBoost performs strongly but not as well as SBM or logistic regression in the dataset. The performance similarity to gradient boosting suggests that the boosting models may be less suited to this dataset. Before comparing the models, I want to discuss about how we use hyperparameter tuning to improve their performance. We used grid search as CV. Systematically like test different combinations of parameters and select the best performing model configuration. For SBM, the best parameters were C like 15 and gamma was 0.01, which significantly improved the decision boundary. For the decision tree, grid search suggested increasing the tree depth and adjusting the minimum samples per split and lift to reduce overfitting. We also tuned gradient boosting by selecting the best learning number of estimators. Random forest was manually tuned by adjusting the number of trees and maximum depth. Overall, hyperparameter tuning helped optimize our model and led to better accuracy of ROC performance. So here is the combined ROC curve for all models. The ROC curve measures a model's ability to distinguish between malignant and benign tumors across all possible classification thresholds. We see that the SBM has the highest AUC score of 0.98, making it the strongest performer in the term of overall separability. Logistic regression follows closely with an AUC of 0.97, and decision tree also performs well with an AUC of 0.96. Ensemble models like random forest, XGBoost, and gradient boosting all cluster around and AUC of 0.95, showing strong but slightly lower performance. Kinnan has the lowest AUC at 0.93, which matches its lower test accuracy and higher false negative count earlier. And this slide compares the performance of all model using both accuracy and ROC scores. We can clearly see that the SBM is the best performing algorithm, achieving the highest accuracy of ROC. Highest accuracy and ROC. Logistic regression is also very good, very strong, and close behind SBM. Ensemble methods such as random forest, XGBoost, and gradient boosting give consistently good performance across both metrics. Kinnan is the weakest mode in our comparison, which aligns with its higher false negative rate. The overall comparison confirms that the margin-based algorithms like SBM work exceptionally well for this dataset. In addition to these insights, we also faced a few technical challenges. First, managing class imbalance was important because it affected false negatives. Second, some models, like especially tree-based ensemble models, tended to overfit, so we had to carefully tune them. Finally, identifying optimal hyperparameters required considerable experiments and all. Coming to the conclusion, classical machine learning models performed exceptionally well on the breast cancer detection. The support vector machine emerges as the most effective model due to its high accuracy, highest ROC score, and low false negative rate. Logistic regression also performed very strongly and provide a reliable interpretable baseline. Ensemble based models such as random forest and XGBoost perform well but show slight sign of overfitting. Overall, the experiment highlights how crucial pre-processing such as scaling and cleaning the data is for achieving high model performance in the medical predictions. For future improvements, we can use cross validation to get a more reliable estimate of how well the models generalize. Another direction is to explore deep learning models such as artificial neural network ANN, or even modern architecture like TAVNet, to see if they outperform classic machine learning on this dataset. Since medical datasets sometimes suffer from class imbalance, technique like smooth can be applied to reduce bias toward the majority classes. So now I like to conclude my presentation. Thank you everyone for watching.